My name is Scott Nance. I'm a senior printed circuit designer at Optimum Design Associates. I am not a presenter, and I'm about to demonstrate that shortly. So I am a PCB designer with 30 years experience, and I'm very proud of that. I'm very excited to be presenting practical analog and RF and mixed signal PCB design. This presentation is based on an article written by my friend and all-around guru, Brendan Parise. I highly recommend reading his article, and we have other articles, and that can be found on our website at blog.optimumdesign.com. It may not be up there now, but it's going to be up there shortly. And many of the subjects that we're going to talk about in this presentation are too large for this 1 hour presentation. So they're going to be broken up into many articles. And again, I highly recommend that we review those at our website. So if you could, please hold your questions till the end. We're going to be short on time. There's a 10 o'clock right after this. And I will be available to answer any questions or try to, or have someone even more efficient and answer those questions. We're going to be in booth 308, and that's Optimum Design. We're right around the corner. So you may be wondering what this presentation is about. So in the last 15 to 20 years, or up into about 15 to 20 years, each one of these technologies was on its own board. We had an RF board, a digital board, and such, maybe boards, multiple boards, but they were in their own cabinet and they were in their own chassis. And now they're all on one board, and they fit in your pocket. So everything but RF was slow, and it was very slow, but I say that in hindsight because we thought it was fast at the time. So because they were in their different compartments, we didn't really care that much about the effects of the digital and the analog being so close together. Now it's a different story. When I was designing an RF board, I was designing just an RF board, and designing digital, just a digital, and it was slow. What was very separate and very slow is now all on one board and is blindingly fast. It is getting smaller, and it is also getting faster. So we're going to discuss issues that you need to consider more with a mixed signal design than you do with a straight digital design. We're also going to discuss considerations for mixed signal, such as power delivery, bypassing, stack-up, and floor planning. And then we'll talk about methods, design layout methods that have been used successfully over years. So loss and noise, in particular, are concerns in digital, obviously, but they're not the same concerns or to the same extent as they are in analog. So it is important to protect the analog system from the effects of the digital system, not so much vice versa. Okay, the data. Obviously, digital square waves are actually sine waves, summed with an infinite number of harmonics. And obviously, digital is in ones and zeros. Analog, the frequency can actually be the information itself. Information integrity. Digital logic has a threshold, and some logic families and some digital devices have more tolerance to degradation of these parameters: frequency, amplitude, and phase. Amplitude can affect the quality of the digital signal. Frequency can affect the data rate, but neither are the data. Amplitude, frequency, and/or phase in an analog system typically is the data. So digital as a noise source. Large amounts of voltage transients, and the faster we switch, the more higher harmonic content we get. Analog as a noise victim. Low noise margins, low levels, and on top of that, analog nodes could be at a high impedance. Very prone to pick up noise. So old school analog engineers realize that modern digital really is taking on some of the old analog and RF problems. Skin effect, fiber weave effect, conductor loss, dielectric loss are all things that used to be in the RF domain and are now in the high-speed digital domain. So analog is the key to understanding high-speed digital. And low voltage, high-speed digital, for instance, a core voltage at under 1 volt, has a very low tolerance to noise because its threshold is at a low voltage. Here's some commonly accepted boundaries, although some will argue that microwave doesn't start until 6 gigahertz. We are also in the age of terahertz, which would be 300 to 3,000 gigahertz. It's either called terahertz or tremendously high frequency. So let's talk about analog and RF issues. Digital issues are well known. Diff pair skew, DDR timing, so on and so forth. We're not here to talk about digital issues. In analog, these systems are far more concerned with efficient transfer of power. So obviously they're more prone, or we're more concerned with a lower tolerance to loss. And in noise issues in a mixed signal design, they're created in large part by the digital circuitry, and with analog being susceptible. And of course, in analog and RF, clean power is essential in an analog system. So dielectric loss is a function of the material, and as a PCB designer, you really have no control over that except the selection of the material. Dielectric loss is loss to heat, and it's also proportional to frequency. So the higher frequencies have higher losses, or we see higher losses. And it's a function of the material's molecular structure, the shape of the molecule, the resin type and content, or percentage of resin versus weave. It's very important to be in contact with your fabrication vendor to get dielectric constants as part of the fabrication process, and not just calculating them yourself without any fabrication vendor involved. So probably the biggest contributor to loss in an RF system is return loss. Return loss, reflection coefficient, and VSWR or VISR are all measures of impedance mismatch. From the entire system, from the source, the transmission line, which the PCB designer is in control over, but the connector, the cable load. Return loss is caused by any impedance mismatch in the system. And as the PCB designer, the transmission lines are what we can control and what are important to keep a continuous impedance. And just to throw one more thing in there, the impedance is also frequency dependent. So the higher frequencies change the impedance, the characteristic impedance, as well as the source and load impedance. Throwing this formula in, we're not doing too many formulas. This is a formula you'll probably never use. This is for the reflection coefficient. And it's a ratio of the reflected wave over the incident wave. To me, what's interesting about this is the same formula is the characteristic impedance, the ratio of the load impedance and the characteristic impedance. And the point here is that what we do to our transmission line and impedance mismatches are the exact same as a reflection. So an impedance mismatch is a reflection in RF. There's another ratio that's commonly used, and all you RF or ham radio operators understand VSWR or VISR, because this is a calculation for RF antennas in the ham radio world. And it's a ratio of the, again, of the standing wave and the incident wave. And here's a picture to show what VSWR does and the two effects that we have of an impedance mismatch. So in the first picture, we have a load impedance that's higher than the line impedance. The line impedance is shown as 40 and a half ohms. And the load is 50 ohms. And in this particular case, the reflection back, which is the blue, happens in phase with the incident wave. So it has a cumulative or an additive effect. And we get a standing wave of 1.1 volt with a reflection of 0.1 volts on this incident wave of 1 volt. The opposite happens where the load impedance is lower than the line impedance. Here we have a load of 40 and a half and a characteristic impedance of the line of of 50 ohms. Here the reflection happens out of phase. And so this loss or return loss is a loss in amplitude. We are designing for an impedance match when we're laying out the board. Skin effect is another type of loss. It effectively raises the resistance of the trace and thereby creating heat. Higher frequency skin effect is more pronounced. And what it does is it tends to make the current flow in the thin outer portion of the trace. And of course, the higher frequencies, this happens more. Copper roughness can compound the issue, creating a longer path for the signal. And this can add inductance and can affect timing as well. So something to keep in mind. And one skin depth in copper is 2 microinches. And if you take 3 skin depths, which is only 6 microinches, a very small dimension, it carries almost all the current. So you can see how the current is forced into a very small piece of copper at high frequencies. We're only talking about 1 gigahertz. This is very pronounced when you get up in 77 and 100 gigahertz. This picture shows some skin effect and the way that copper carries the full amount of current across the copper, or the full copper is used to carry the current at a low frequency. And as we go higher in frequency, it tends to be forced to the edge of the copper, tending to condense or around it's going to be closer to the reference plane as well. And that's what that picture is showing. It's also a good indicator of showing how copper roughness adds inductance because the line length is now longer. So that's why there's so much talk about smooth copper. Smooth copper is going to be a shorter distance, and we'll talk about that in a second. EMI is one of those subjects that we just can't get into really here in this presentation. It's worthy of many books, and PhDs will argue every point of this. The only 2 points I want to drive home for a PCB designer are these 2 causes of EMI, or potential causes. Current loops. As a PCB designer, we want to identify all the current loops in a system. The power supplies, the local power supplies, the bypass caps, all the signals. If we can identify all the current loops and make them as small as possible, that's advantageous. And the other thing is multiple system grounds. The way I explain this is a switching signal crosses a mode and then references 2 grounds, maybe an analog ground and a digital ground. This creates a voltage potential across the 2, and this can become a patch antenna. So large loops become efficient loop antennas, and multiple system grounds can become efficient patch antennas. 2 things to think about when we're trying to design for low EMI in a mixed signal design. Noise coupling, again, another huge subject. We will have an article on this on our website someday, but the only things we want to talk about now is that the 2 main causes of noise coupling, or the 2 types of noise coupling, are conducted and radiated. Conducted maybe being through the actual copper trace supplying our analog circuits, where a digital circuit has created noise on that. And the other one is incorrectly routing digital lines into our analog area. These would be sources of conducted noise. Radiated noise coupling would be caused from digital being too close to our analog circuit. And we want to identify the victims and aggressors. And this could be complex because a victim or aggressor can be either analog or digital. And any given signal, whether analog or digital, could be an aggressor and a victim. Another huge subject, we're going to say 2 different types of shielding and leave it at that, but the Faraday shield blocks your E field, which is your electric portion of the electromagnetic wave. It's also called capacitive coupled. And it displaces that and tries to return the current back to its source. So the point is, the shield doesn't just take this energy and dissipate it into thin air. It has to try to get back to its source. So looking at the path from your shield or items inside your shield and how that noise might be returned back to your ground input on the board, you don't want to run that energy through another sensitive circuit. Magnetic shields are a lot less common. They're very difficult and very expensive. They need ferrous materials. And in that case, the shield converts that energy to heat. The point about chassis resonance is that an odd-shaped shield works better. It doesn't resonate as much. The worst-case scenario is a cube where all the walls have the same dimensions and are empty, because then you get a resonant. It's more likely to have a resonance. So bypass and decoupling caps. They each have discrete functions, and we're going to talk about that in a second. You may connect to them differently. Planes and traces for powers in an RF circuit. Typically in a digital circuit, you're going to use power planes for a power delivery system. When it comes to RF, you may have a local power supply and a filter that's very close to this circuit. And so in that case, it's typical to use a routed trace or a fat trace with low inductance to hook this up. The reason being is that small planes can become effective patch antennas because of their proximity to a larger plane. And so if you do need to have a small plane to power your RF circuit, in that case, it's best to use an irregular shape. Again, to take away the effectiveness of becoming a patch antenna. And precision circuits may reside on your board as well. These are very prone to noise on the power supply and require great care. So in this picture right here, we're going to talk about decoupling a little bit. In this case, we have a digital chip with a lot of high-speed I/Os on the left. Now, if these I/Os are switching at a very slow speed, this power supply that's at some distance away might be able to supply that. That we might be able to supply the current fast enough for those slow switching signals. But if those I/Os are simultaneously switching and switching very fast, it is unlikely that that power supply will be able to supply the current demand in the time needed. And what happens is that we get a voltage drop on the plane, and that is creating a voltage transient. That voltage transient is a manifestation of demand for current. So the initial current must come from our interplane capacitance or our decoupling caps. So the lowest value cap is placed closest to supply the high-speed current or the highest speed current demand. And it's doing that through the lowest impedance path, which is our power delivery plane. The decoupling cap discharges to that plane and ideally creates no need for a voltage drop on the plane since it is discharging its energy. So for a few pico or nanoseconds, you've effectively decoupled your device from the power supply. Until the power supply can catch up. And the point here is that you've contained the transient locally to this device up to the decoupling cap. So the point of decoupling is preventing the noise from getting on the plane to begin with. Bypass caps, here we have an analog device. Bypass caps, as opposed to decoupling, is more about removing existing noise on the power supply before it gets to your device in the first place. So bypass caps are used to provide a low impedance path to ground for our noise. And we pick our bypass caps to effectively have a low impedance path at a particular noise frequency. And the frequency spectrum of noise is typically probably going to be too broad for one bypass cap to handle to have a low impedance enough path. So that's why you have bypassing networks of several different values of capacitors. And we'll talk about bypass networks as well. So I like to think of decoupling caps to be more pertinent to digital designs, and bypass caps being more pertinent to analog designs, but not exclusively so. So useful frequencies of a bypass cap. Every capacitor on their spec sheet will show their self-resonant frequency. And a bypass cap is only effective up to that self-resonant frequency. Parasitic inductance inside the package of the capacitor is called ESL. And because it is inductance inside a capacitor, an L and a C will form a resonant circuit. And this will happen at some frequency. Parasitic resistance inside the capacitor body itself as well is called ESR. And we're going to show you just a little demonstration of how ESR can be tweaked to create an effective bypassing network. Again, a network is several capacitors at several values. Just an example, not to be taken verbatim, but these are some examples of some capacitors and their self-resonant frequencies. The point being, maybe as a PCB designer, when you're looking at your RF circuit, if you have very low-value puff caps, it may be a good sign that you are dealing with a high-frequency circuit or a circuit that you're concerned with high-frequency noise. So about bypassing networks. This is just an example. We're going to show two capacitors here, a 4.7 microfarad cap and a 0.1 microfarad cap. And these are both low ESR caps. You see each capacitor, the smaller value cap, has a low impedance to ground for frequencies around 20 megahertz. And the 4.7 looks like it's around 2 megahertz. Very low impedance path, very sharp slope. But we're missing some of the noise frequency bypassing we want in between. And one solution to that might be adding an additional cap, but sometimes there isn't room for that. So just to show that by using a higher ESR cap, which is typically called not as good a cap, because low ESR is something that we're told is good. In this case, a higher ESR cap broadens the effective frequency range for bypassing of your entire network. We no longer have a spike across 20 megahertz. And so long as this impedance is lower than the internal impedance of VCC to ground of the device we're trying to decouple or to bypass, then this is an effective bypassing network. So these are things to think about in mixed signal design here. Talk a little bit about materials, some processes, and some types of impedance controlling. These are taken straight out of IPC 4101. So these are standard material considerations or categories. CAF resistant is something that's really the limitation to us miniaturizing using PC boards now, because it's interlayer electromigration in a laminate. And it's typically a function of the via wall to the glass and copper molecules or copper atoms migrating and causing either leakage or shorts in our boards. The smaller boards that we're doing with the smaller annular or the smaller clearances to planes, we can look at materials that have a higher CAF resistance. The point being here is that a lot of times our electronics, we're thinking just of low dielectric constant and low loss. But that's only one category in many categories of materials. And the point being, being very close in touch with your fabrication vendor. He's going to be the expert. He does this every day, and he can come up with many, many solutions. These are some more considerations when it comes to materials. Loss tangent is the same as dissipation factor. Relative permittivity is the same as a dielectric constant. One's usually an engineering term and one's manufacturing. And something that affects both of those is the glass composition and the glass to resin ratio. This is something you may not know beforehand, how you're building up your board. So again, the fabrication vendor should be really part of this. He should be the one dictating this, because you possibly don't know what the resin content is going to be. So you're using dielectric constant numbers from a previous board that may not be pertinent to the board you're working with. Another parameter coming up that we're going to see in spec sheets a lot is thermal coefficient of E sub r, or how the dielectric constant is affected by thermal by thermal expansion. We're calling these lead-free assemblies now. We used to call them RoHS compatible, but more materials, more hazardous materials are being added to this list. So no longer can we just say if it's lead-free, it's RoHS. Terms used are lead-free assembly compatible. And I thought that had to do with T sub G. That's the melting point of the glass in any given material. But some materials that are green and lead-free compatible actually have T sub Gs at 170 or below. I'm not really sure why. Maybe someone can help me after and tell me why that these are being approved. Moisture absorption is a huge problem or a concern with materials because that affects dielectric constant. It also affects reliability. Copper adhesion, multi-laser ablation just means if it's HDI compatible. UL certification has to do with flame retardation. There's some blanket statements that we do not make because polyimides, we say they are not flame retardant, yet they are. There's 94VO toughened polyimides. There's different classes of certification. And when it comes to outgassing, this is for space. The three things we're concerned with there is total mass loss, volatile materials, and water vapor recovered. So here's some typical materials. The first one is epoxy woven glass. That's our FR4s. That's our Isola 370HRs, our FR408s, et cetera, et cetera. I call them FR4 grade because there is no material called FR4. You cannot look up a dielectric constant because no one builds FR4. It's a grade and it's the holy grail of manufacturability and cost. The next four, the BT epoxy, cyanide ester you might recognize as being the Nelco N4000 series or 6000 series. The PPO and the PPE, which you may know as Megtron 6, those are called blended resin systems. They're based on the FR4 manufacturability, but they have different properties, maybe better thermal, better dimensional stability, dielectric constant, chemical resistance, so on and so forth. The next one, the non-woven aramid, is called it's a paper, but it's not the paper as you might think. It's in the same class as Kevlar. So very strong weight to strength ratio. Polyimides, Arlon's a big, if you're into RF, Arlon's a great manufacturer of the polyimides and the aramids, although they have many different materials. You may be familiar with the Rogers 4000 series, these synthetic rubbers. And then I'm showing you a green material. Thermoplastic might be something for very rugged and very tough environments. Thermoplastic is opposed to a thermoset. Thermoplastics are melted and remelted. Thermosets get melted and are set. The spread glass I put on there, that's just a really proprietary thing for this, specifically made for 100 gigabit transfer rates, digital, like backplanes. And it's coupled with ultra smooth copper, very proprietary and very specific in its use. The next four, the PTFEs, are the Teflons. You'll see terms like woven glass reinforced, random glass fiber, lightweight woven glass. These are all very proprietary things to add structure to the Teflon, because Teflon is really good at having low loss, but it doesn't have structure. And those two things are really proportional to each other. So the fiberglass inside your PC board, it's common to see 1080. If you're not calling out what your 1080 is a very common weave. But as you can see, a trace crossing across that, or a trace over that, we'll see a different dielectric constant when it's over the weave as opposed to over the resin. So 7628 as opposed to 1080 looks like something that you could route a trace over and have a really smooth dielectric constant across the whole transmission line. The only problem with using 7628, especially when you're using a high-density digital design, is that it's very thick. It's almost 7 mils thick. So these are the common weaves. And the thing I want to point out is that there's something called spread weaves. They're thinner. You can use them in your digital designs. There's something called 3313. There's many others. The only problem is I don't know, for a given material, not every spread weave is available. So by asking your fabrication vendor if you have a spread weave in that, he may guide you to another material. And each of these fabrics are made up of a yarn. Those yarns are called out with this identifier, ECD 45010 for the 1080. That's very popular. And here's what that name comes from. The E is for E-glass, continuous filament. The D is 5-micron fiber, of course. And here's some common fiberglass strands and their thicknesses. I read somewhere that in a common like 6x8 FR4 board, there's up to 500 miles of fiberglass strands if you let them end to end, because each yarn is made up of a strand, and each yarn is creating a fabric. The compositions of different fiberglass is very important when it comes to dielectric constant. So E-glass is pretty much exclusively used in PC boards. There's very few boards or board materials that do not use E-glass. And that chemical composition is, I'm showing you the silicon dioxide, the calcium dioxide, aluminum, barium, sodium and phosphorus, magnesium, iron oxide, and titanium. The point being is that there's been a lot of work to try to come up with a different kind of glass. And the NE glass is a good example. That's a Natibo glass where they changed the value of the calcium and the barium. And again, it's called Natibo glass or NE glass. If you look at the Nelco, they'll call it SI glass, but it's a proprietary thing because they are using Natibo glass. The two that come to mind are the Nelco N4000 13SI and the Panasonic Megtron 6. They both will use SI glass. And the point of NE glass. The point of NE glass is that its dielectric constant is 4.6 as opposed to E glass at 6.2. So this is to help mitigate the fiber weave effects you see at high speed. Other fiberglass glasses might be S glass, D glass, C glass. Those all mean something. S for strength or structural. D was developed for a lower dielectric constant. C glass is chemical resistant. Quartz is not made out of quartz. It's made out of almost pure silica. Silicon dioxide, almost pure. And of course, the aramid is another type of glass, although it isn't really glass. Again, it's a paper in the same category as Kevlar. The reason E-glass is used almost exclusively in all PC boards, including the high-end ones, is cost. The S-glass is 5 times the cost of E-glass. The D-glass, which was developed for lower dielectric constant, is 20 times the cost. And quartz is very hard to make, and that is 40 times the cost of E-glass. So there's an equation for figuring out the dielectric constant of a laminate. And that really, the weave impact, because it changes the amount of resin versus weave, really affects it, unless you're using, of course, the lower dielectric constant glasses, and then that'll help mitigate it. So if you look at a material data sheet, it's going to give you a dielectric constant of that material, but it's just generic to give that to you at a 50% resin content. So until you really know how your board is being built, we don't really know what the dielectric constant is of any particular given layer. And just an example of the impact of weave on a particular material. This is not the SI version I'm going to show because that would be less. But two extremes would be a 106 weave and then the 7628 weave, which is very, very full. So those are two extremes, and you see the dielectric constant changes from about 3.3 to 4. It has a big effect, but not as big effect as the molecular structure. So lower dielectric constant materials aren't always better. Rogers, as far as a material manufacturer, is real unique because they provide microwave engineers with multiple, they have a series. It's called like the 4000 series or 3000 series, 6000 series. And that series will have incremented dielectric constants. So a microwave engineer can use that because when you get into higher dielectric constants, that allows you to have smaller and smaller features for your microwave components, which are sometimes odd shapes. And the other thing to note is that dielectric constant affects the wavelength. So the higher the frequency of a signal, the shorter the wavelength. Loss. Loss is also called the dissipation factor. This is just a sample of some common materials ranked by loss. And it's no accident that the higher loss materials are easier to build. The FR4 grade materials are typically around 12 thousandths to 0.025 as a dissipation factor. And then we'll get into then there's some lower, called low loss, which are they're still easy to manufacture, but they're the next step up. You're going to recognize some of those, the FR408s. Maybe one thing to keep in mind, or one thing to keep your eye on is this Isola I-Speed. It's got better properties than the FR408, and it was designed specifically to replace FR408. FR408 is a very common material at this range of cost and loss performance ratio. And I-Speed is something that's really it's been developed to take care of or to replace FR408. And as you see, it's really knocking on the door of the Nelco 4000 SI as far as loss, and the Megtron 6. And here's some performance materials. These would be these would be considered more RF and very high speed. Straight to the bottom, 0.004 is a loss tangent. That is effectively zero. And you know when you're that low, you're using pure Teflon. Because Teflon has pretty much a dielectric, or it pretty much has a dissipation factor really close to zero. But it needs some kind of structure because it's very low loss, it has no structure. So in this case, the TacLam Plus is metal backed. And that's how it gets its structure. These are types of copper treatments or are copper foils. So ED copper or electrodeposited copper is our typical copper that is mostly used. In the old days for RF, we used to use rolled copper. And we're trying to get away from that because it's very expensive and there's just huge manufacturing issues with it. So it's still good in flexible circuits, but we're trying to get away from it in the rigid PC boards. It's pretty much considered a custom build now, which wasn't the case in the old days. And the reason that it is now is because we're trying to replace it with treating of the electrodeposited coppers. So reverse treated or drum side treatment is really all about getting the copper smoother. VLP and micro LP, there's other names for this, and some of them are proprietary, some of them don't have any difference, but the Rogers Low Pro is a very low profile with an oxidated layer. And then VLP2 is something that people use if it's got 2 microns or less of tooth. And copper adhesion, I just want to point out, some materials are bonded better to smooth copper. Teflon bonds very well to smooth copper. This is about etch tolerance. Because trace width affects impedance, a wider trace is less affected by these tolerances. We can mitigate the problems of etch tolerance by using a smaller copper weight, but in doing so, we're adding resistance. And the typical treatment for these copper plates on an external layer will be ENIG or ENIPIG, and those provide uniform thickness and complete coverage. Via in pad is preferred. It's not an exotic process anymore. And VIPO stands for via in pad plated over. In our fabrication drawing, we'll call for that to be planarized flat. The reason we want to use via in pad is inductance to the leads of our components. You can't get the inductance any lower than putting the via right in the pad. And if we're using HDI or laser drilled vias, that's even better. So examples of transmission lines. Transmission lines are defined by their length relative to the wavelength of the signal being transmitted on them. So the first time this really came into play was the telegraph. So that's why the transmission line equations are sometimes called the telegrapher's equations, because they're the ones that really figured out the problems we're having with reflections and transmission lines. So all those formulas have been done years and years ago. Other transmission lines might be the twisted pair they might use for DSL, or a coaxial cable used for cable modems. So those transmission lines equate to transmission lines that we design on our PC boards, and they're called planar transmission lines. Many derivations of each of these, but these are the three common ones I can think of. The microstrip, which is a transmission line over one solid ground plane. Strip line would be sandwiched between two planes. And coplanar waveguide is a transmission line with ground planes on both sides of it. So it's on the same plane. It's very typical to have a ground plane underneath this. That's typically the only kind of coplanar waveguide I've seen. But that's called a grounded coplanar waveguide. And of course, there's electromagnetic fields associated with each of these transmission lines. So there's two of them. There's going to be your E field. Again, the capacitive coupled. They're terminated into the ground plane, ideally. And the H field, which is the magnetic fields surrounding it. Both of them comprising your EM, or electromagnetic waves. So some pros and cons to each of those. Microstrip traces are typically wider. That's a good thing for skin effect loss. Etch tolerance, we discussed that. One of the cons of that is because they're wider, they take up more space. And we're trying to miniaturize everything, so microstrip is sometimes, in some instances, being replaced with strip line for that reason. Microstrip dielectric can be air, or half of it. If it's not coated, if it's not embedded, then air is the other dielectric on the other side of that trace. And so all the calculations are using something called effective ER. And of course, the main advantage of microstrip typically to all our old RF boards, they were all 2 layers. So the signal, the transmission line, the signal doesn't see a via or the inductance associated with that. All the components, connections, everything are on one layer. And that allows, if there's no vias, that means the bottom layer is a complete solid ground plane. And that's typically all the old school RF or microwave circuits that we've seen in the past. Pros and cons to strip line traces. Strip line requires multiple layers, right? Because we have a ground plane on top and a ground plane below. So we need a minimum of 4 layers to do strip line. Having said that, we need a via to make those connections. And via barrels can be inductive. They can also be stubs. So we need to take this into account at high frequencies, either with layer usage, possibly using the bottom layer to minimize the stub on the via barrel, or by back drilling. Another advantage of strip line is because their nature of being between 2 ground planes, they're going to radiate a lot less noise. They're also less prone to picking up noise. Some proven methods. Here's where the synthetic rubber hits the road. This is where layout is. Circuit blocks and floor planning, stack up. We're going to talk a little bit about power delivery, and then a little bit about routing. Of course, when you start your layout, mechanical drawing is going to dictate where all the fixed place connectors are. RF antennas, for instance, shields, cavities. And then we're going to use the schematic, of course, to identify the critical circuit blocks and paths. Data sheets are very important, of course, for every digital device, but also for RF to see what the manufacturer recommends on how to connect. Important part about circuit blocks in an RF world is because rooms, by looking at the schematic, you may not be able to tell that if a filter is gigantic or small. And so until we really define what the rooms look like, what the components look like, and get a rough placement together, we really don't have a good idea if we can fit this in our shields and how we're going to be able to do this. We might be able to swap rooms depending on the size of each of the components. And the RF input, which may be your antenna, is going to have extremely low level and it's going to be extremely sensitive. So we want to keep all switching noise or any noise source as far away from that as possible, including other analog signals. Quick view of a floor plan. If you see, if you're familiar with moats, this is separating or a ground slot between the two realms, the digital and the analog. There's a bridge formed across that where the two planes meet, and all signals going from digital into the analog roll across at this one point. This is really going to force you to design this board right, because you're going to be able to design where the return paths for all the signals across are. Once you've done that, it's very possible you're able to get rid of the split in the ground planes and use one solid ground plane. That's being recommended a lot now. But having said that, if you're going to get rid of the ground plane, start this way. This will force you to do it right, and then you can get rid of the slot after, because it's been done right. Very key in mixed signal is isolation. Of course, if it's on the same layer, it's in the XY axis. If it's above something else, it's in the Z. And in most cases, we're thinking about X, Y, and Z axes as far as isolation. Shields really come into this, because now our shields in our small mixed signal designs, like cell phones, for instance, are very small. They're very low height, and they can affect the impedance of a trace. So this comes into play under isolation. So if we're talking about just XY axis, this is just an RF section of the board as opposed to a digital section of the board, with our ground plane slot and a bridge maybe being on our bottom ground plane, depending on where the signals cross. We want to have a reference plane for where the signals are crossing. In this case, layer 6 would be where they're crossing, because that's adjacent to the bridge. This would be a Z-axis isolation, where we have RF on the top of the board and digital on the bottom of the board. And the idea is to increase the isolation between the two as much as you can. Even though those are two ground planes next to each other, we do not want those coupling. And this might be a very good situation where you talk to your fab. This might be a situation you see where we have a Rogers material used for the top of the board and an FR4 material used for the bottom for the digital. X, Y, and Z axis, self-explanatory. The vias that come up to the RF should only be associated with the RF. This is a case where we're seeing blind vias just to keep the possibly higher density digital on the bottom of the board isolated from the RF. And when we stack up our RF board, layer 2 is RF ground always. It may come, there's situations where we are referencing layer 3 to widen our RF traces, but in areas that we're not doing that, we're flooding it with RF ground. So layer 2 is always ground. It just may be that layer 3 is as well. And then I'll show you a couple stack-ups, an example stack-ups for RF and some mixed signal stack-ups. I'm not going to show you a 2-layer RF board because that's pretty explanatory. That's a microwave trace over a full ground plane. This is a 4-layer RF board. And in this case, we have microstrip traces on the top with a full RF ground plane on layer 2. And then layer 3 is a microstrip layer or a power delivery layer or additional RF signals. Might be your LO and your IF signals that are lower priority than your high frequencies that are microstrip on the top. Just another example of another RF layout or another RF stack-up. In this case, you would have a separate power delivery plane and then strip line traces on layer 3. XYZ mixed. So this would be for a higher density digital design. And each one of these are the same. The point is that we want the isolation between the RF and the digital. We're saying at least 15 mils. And because when we're building boards, we don't want them to warp, we make things symmetric. So it is if we have a thick core for isolation, then we have a thick core on the opposite side of the board. We may build this up symmetric, but we may end up clearing some of the digital layers underneath it and not even using them. But the idea is to make it symmetric. 12 layer, these are just, so each one of these, the 12, the 14, and the 16 layer stack-ups are exactly the same, except each one is for more incrementally dense digital design. More routing channels for your digital. The same isolations apply. When it comes to placement, we have to separate the analog and digital, and we just have to be really aware of how we intend to do that. Shielding, XYZ isolation, so on and so forth. And when we're placing RF parts, inductors do not go parallel to each other because their magnetic fields will couple. So we try to place them at right angles or far from each other if at all possible. And the blanket rule in RF is to keep the input short. That's not always the case. There are many times when you want to keep the output short. And some of the instances I can think of are an attenuator or a filter where you want the output to be short. This is shown as an example of how to place the power supplies in a mixed signal design. The switching power supplies for the main power are going to be up by the power connector where the power comes into your board. You may have another switching power supply for the core voltage for your FPGA. It might be a 1-volt synchronous buck switcher. And then typically you're not going to see switching power supplies in your analog and RF section. Those are going to be linear. They're going to be linear, they're going to be filtered, and they're going to be very isolated and small. That's some of the, we were talking about hooking those up with traces as opposed to planes. This is priorities on, this is a small thing, this is priorities on how to place your components. The lowest value caps go closest to the pins that they're made for decoupling or bypassing, and so on and so forth. So the bulk capacitors are obviously farther away than the low value caps. Here's an example of how we want to do our fan-outs for decoupling caps at an FPGA. V in pad is preferred. We also like to use for a bulk capacitor, we're going to use multiple vias. And we like the idea of having the traces come out so that the vias are adjacent on one side of the capacitor. And what that does is it decreases the current loop happening at that device. Some examples of decoupling caps at a QFP. One with a big thermal pad that doesn't allow you to have vias underneath, and one that's open. And both these examples show via in pad. And I like the example, these are also very effective bypassing because, again, bypassing, well, we'll show you right here. Multiple vias. So in bypass caps, this is an RF amplifier or an MMIC. And the way that's connected different is bypass caps, we route the power through them. Because again, we're trying to take noise off the power supply that's already existing. Again, the lowest value cap is closest. When it comes to fan-out, via and pad wherever possible. And when you can't use via and pad, we want to widen the traces as much as possible. And this is to not add inductance. This small thing is a cumulative thing. And as far as the RF signal, the transmission line, if we're using strip line traces, we have to use a via. So if it is via in pad, we want to be real careful where that via is. And what I mean by that is we don't place it in the center of a land. We have it at the end farthest away. And what that's doing is minimizing the stub. So here's an example where so these are corners used in RF and in transmission lines. Basically, there's two kinds of corners. There's rounded and mitered. There's a formula for the mitered corner. And this example shows two reasons that you would use a mitered corner. One of them is very sharp bends. Very sharp corners are done with miters. And the other thing that's done with miters is a very exact distance for coupling. That works very effectively there. These transmission lines also have a very short period of time where going inside that shield, they use a coplanar waveguide or a grounded coplanar waveguide formula. The rest of it is microstrip. And these traces these traces are referencing layer 3, so you can kind of see that layer 2 is cleared out from underneath them. After the first device, they start referencing layer 2, and you can see that because the trace is much skinnier. So when it comes to rounded corners, so long as the radius is over 3 times the width of the trace, it's effectively a straight line. If it's under 3 times the width of the trace, you can get coupling between them, and so it is not typically done for sharp corners, and that's the reason. I say 3W, but that's probably a number you got to keep away from. As soon as you get at 3W, you want to think about either moving your components or using a mitered corner. Stubs. We want to minimize stubs, of course, and I mentioned that we can minimize them by layer usage, which would be if the via is taking our signal from the top layer, we might want to use the bottom layer, because that via barrel will no longer have a stub. Stubs are very important in RF because even a small stub at high frequency matters. And the last thing, any metal can resonate at a quarter wavelength. We hear this rule of quarter wavelength, but that's, again, a number we want to stay far away from, because if our metal is resonating at a quarter wavelength, that means even a chunk of ground plane we think is being used for isolation can become a transmission line. It becomes reactive at a quarter wavelength. And it becomes reactive at a quarter wavelength of the current flowing through it if it's not terminated in its characteristic impedance. And every half wavelength after that. So with our RF circuits, we typically, to try to minimize the loss due to radiation, we want to flood the RF circuit with ground. And when we do that, we don't want, if at all possible, we don't want thermal reliefs on any of our pads. Rule of thumb I use, if it's an 0603 passive device or smaller, I will use thermal reliefs, but I'll use them wide as possible. And this is something you want to talk to your assembly house about. 0805s and 1206 typically don't have the same tombstoning effect when you have at least a symmetrically buried pad in plane. And when we flood those grounds, we want to keep a 3H to 4H spacing to the plane. H is the distance to the next plane, so 3 to 4 times that, and we do that to not affect the impedance of that trace. And the last thing we do with our transmission lines is we have offensive vias on both sides of it. We wall that in. There's some rules of thumb there as well. Space vias at an 1/8 wavelength. I don't like that rule because underneath that you're too close to the quarter, so you've already got leakage and you're already getting close to being reactive. So I say 1/8 wavelength of frequency of interest maximum. What I'd recommend for a complete isolation, and why wouldn't you want this, is you should be shooting for more like 1/20th wavelength. And here's how you'd figure out what that wavelength is. Because as I said before, dielectric constant decreases the wavelength. So many times you'll be talking about a wavelength and not realize that someone's talking about an air. So this is a calculator we're going to have available on our website. And it shows some typical microstrip and strip line traces in an FR4 environment, what their wavelengths are versus frequency. The frequency's down here, and then these are the different wavelengths. So this is a valuable calculator to figure out where we want to space our vias and what can become reactive at a certain frequency in the dielectric constant that we just happen to be using. So we've touched on these issues, but by no means have we gone in depth enough on any of these issues. So I really would like you to investigate these more, and because each one of these can be a presentation in their own right. And the last thing is that all the little things that I've pointed out in this, the little things that you do, the cumulative effect of all the little things you do are a big thing. The via and pad, the added inductance, all these things become a very big issue in RF. And we have another speaker. It's at 10 o'clock. I think a speaker's waiting right now. Let's wrap it up. I'm going to be out here at 3:08. I apologize for keeping you waiting. I'll be out of here in 1 second. Thank you all so much. Thank you.